Recording is on.
Yes.
Hello, good morning.
Good morning, and Paul Ehrlich.
Good morning, Paul.
Let me allow a short introduction of Paul Ehrlich. He is one of the most important microtonal composer, guitarist, music theorist, and he starts in the 90s, in the 1990s already with these theoretic conceptions of how to understand the generalized way of diatonics with his first paper, Tuning Tonality and 22-tone temperament, what leads to this scale what he nowadays named Pajara, but we have also, I think, one time we have sung that in our solfege attempts. And of course, it's not only that Paul has a very is going on with a very deep research in the mathematical side of all these scales, and also one groundbreaking conception he developed is a harmonic entropy algorithm for evaluate the consonance degree of intervals and chords. So, but today, Paul, we have Paul here over the internet connection, and please, please start with your talk.
Okay, great. Nice to see you all. Nice to see you, Stephen. We are burning the midnight oil, or dealing with some ungodly hours here in the United States to join you all in Estonia. So it's a real honor to be part of this event. Yeah, I saw the description online. Let's see, I can share my screen. Does that work? Share my entire screen. Oh, share. Okay. Now I can, I'm going to go to, one of my papers is called The Forms of Tonality. So I'm just going to, we're going to just spend a few minutes looking at that paper, and then we'll go to some slides that I prepared, and then we'll go back to that paper at one point just for a little bit. And I'm going to put the link to the paper in the chat window here, so you can all take a closer look at it on your own time when there isn't so much time pressure, because I probably have about 18 weeks worth of things to say to you guys, but 1 hour, it's going to have to be 1 hour. So we're going to really skip around and go fast. And I'll try to pause a couple of times for questions. So, so in this paper, so Hans mentioned harmonic entropy. So I'll just show you very quickly. Harmonic entropy is a model of dissonance or discordance, we would say, because we're not considering musical context. It's just how the interval sounds and the psychoacoustical effects of the interval outside of any musical context. And this model is based on two things. It's based on theorists named Terhardt, Ernst Terhardt from Germany, and Parncut, who discussed how it is that we hear pitch. When we hear a musical instrument, for the most part, it's producing a whole series of frequencies, a whole harmonic series of frequencies, and yet we hear it as a single pitch. Our brain is programmed, it seems, to find these harmonic series in our audio environment and then integrate them into a single sensation whose perceived pitch is the fundamental, so the root of that harmonic series, let's say.
Paul, sorry.
Yeah.
Did you intend to share your screen again? Because we don't see your screen.
You don't see my screen?
not anymore.
Oh boy. Share your screen, entire screen. I'm clicking entire screen, but then the share doesn't show up.
Then
Share audio.
maybe just choose the file. If you have the file open on your desktop, then you can also choose just the file to show.
Application window. Oh, I see this. Okay. I'm not seeing that particular one.
You have you have stopped sharing some accidentally. So press the sharing again, and
the share is grayed out. The share button is grayed out.
You have to click on the window one time. What you want to share?
Oh.
It's only one. Yeah, it's a little disturbing. I've wondered about that several times.
Okay. Now, can you see it now?
No, I see only the regular.
When it jumps away for some reason.
It jumps away, yeah.
Oh boy.
Let's try it again. If that not works, then of course maybe everybody download the paper and you see which page we have to look.
Yes.
The plan B.
Yeah, unfortunately, most of the slides are not in the paper.
Yeah.
But
let's try to share the screen again. It must work.
Yes, let me try again. Share.
Yes.
Yep.
Yes, now we see the, exactly.
Okay, great. Sorry about the technical difficulties. I guess we should have had a practice run. Anyway, as I was saying, Terhart and Parncut came up with this idea about consonance and dissonance in harmony being sort of a reflection of how we hear pitch. So when we hear different frequencies coming from a single instrument and the frequencies form a harmonic series, we hear a single very clear pitch at the fundamental. Similarly, harmony, according to them, and according to Rameau back in the Baroque period, the famous composer Rameau, also, he was kind of the originator of this idea, that harmony is sort of an extension of, or it can be an extension of the harmonic series, where instead of single frequencies, you have entire notes, each of which have their own harmonic series. But if you arrange those frequencies in a harmonic proportion, in a simple integer ratio, then they will sort of, in some way, evoke harmonics of a missing fundamental. And that fundamental is the root. It's what, musicians, conventional music theorists, for the most part, consider the root of the chord. Somewhat of a simplification, but basically that's the idea of sort of the Rameau theory of harmony and Parncut and Terhart. And so my contribution was to add information theory. Information theory is a branch of mathematics and statistics, which is has become very useful in understanding information in computer science and all sorts of other fields. And the idea of the main idea of information theory is entropy, and entropy tells you the uncertainty essentially of a signal or a system. So the more confusion there is, the more different possibilities you're unsure about, the higher the entropy in information theory. So I'm not going to describe all the details here, but basically this graph here is a depiction of harmonic entropy, the confusion as to the root of the harmony. And the lower the curve goes, the less confusion. So for example, you see a very low dip for 0 cents, which is a 1/1 ratio. And then the next lowest dip is 2/1 ratio, which is the octave. Those you know, and then you have 3 over 1, perfect 12th over here, 3 over 2, perfect 5th. And then progressively, you know, more complex ratios become more confusing to the ear, less clear what the root is supposed to be. And this is a continuous graph, which means that it doesn't have to be a ratio at all. Any interval at all can be evaluated for harmonic entropy. So then we will, so Hans actually asked me to talk about a couple of different things, 22-tone equal temperament, and also Bohlen-Pierce. So Bohlen-Pierce we'll get to a little later, but in 22-tone equal temperament, and I think everything Stephen was talking about, we generally use this assumption of octave equivalence. Now, I'm really going to have to go super fast, but if we apply this idea of octave equivalence to harmonic entropy, or we force octave equivalence on harmonic entropy, I have a model, mathematical model for that. Now the graph looks like this, where every interval and its inversion get the same entropy. So perfect 4th and perfect 5th. This allows you to consider scales without regard to what octave the notes are in, and you still get a consistent sense of how well the notes harmonize with one another. So here we have some lattices, and I think maybe some of you, if not most of you, have seen lattices before. But the idea of the lattice is to show the consonant intervals, the concordant intervals, the low entropy intervals, as connections between notes. So here we have a major triad in just intonation, a pure major triad. So the red connector represents a 3-to-2 ratio or a 4-to-3 ratio, depending on what octave you put the notes in. And then the blue is 5 over 4 or 8 over 5. And then this magenta is 5 to 3 or 6 to 5. So a pure just major 6th or minor 3rd. So here's a major triad, here's minor triad. This is a 5-limit tonality diamond, which is all the notes that form a 5-limit, and this is odd limit now, consonants, 5-limit interval with a given note, which we call 1-1 in the center here. So I'm going to stop very quickly if anybody has a question, and then I'll switch to my slides here. No questions? Okay. So we'll move on, and I'm going to show you a picture of the diatonic scale. And here I'm using, so in this presentation, I'm going to use a whole bunch of different notation systems. So I hope that doesn't confuse you. But here, for this slide, we have standard letter name notation, and we have the conventional major scale. And what this lattice represents, well, if you try to do this in just intonation, and you can construct this major scale with all the connections shown, this would be a C major scale, right? But then the D minor triad here has 2 intervals which in just intonation are going to be off, unless you allow for different versions of every note that are this ratio 81 over 80 apart from each other. So this represents some of the comma problems of just intonation. You either have to have multiple versions of each note, or you have this out of tune D minor triad. But then, of course, the solution that Western musicians came up with in the late 15th century to this problem is to temper out, as I say, this 81 over 80 ratio, this comma or this small discrepancy, by distributing it into small parts that you spread over the other intervals in the scale. So the result of that is that you get a two-dimensional musical system, including octaves as a dimension. And this diagram here is a horogram, kind of like the ones Irv Wilson came up with. Irv Wilson, of course, being one of the great microtonal theorists. And this horogram shows the MOS scales. I think you guys have been talking about those in some of the sessions. The MOS scales of mean tone temperament, mean tone being defined by the vanishing of 81 over 80 in the 5 limit. So we see here, you know, 5-note scale, the usual pentatonic scale, the 7-note scale, which is the usual diatonic scale. And you can see in mean tone, or this particular variety of mean tone anyway, which is called top, the octave ends up a little stretched, which helps things. And the steps are about 193 cents for the major second and 117 cents for the minor second. And of course, the 7-note scale, if you see the lines, the radial lines in this ring that's labeled 7, and you follow them out to the edge, you see the note names. So C, D, E, F, G, A, B. Then you look at the 12-note ring here, and what do we have? We have D, E flat, E, F, F sharp, G. So a 12-note scale, a chromatic scale. And then the next ring is a 19-note ring, which differentiates D sharp, E flat, E, E sharp, F, F sharp, G flat, and so on. What happens if you adjust the tuning so that your octave is 1200 cents and your fifth, which is the generator here, is 700 cents? Then you get 12-tone equal temperament. D sharp and E flat become the same. C sharp and D flat become the same, and so on. So let me just see if anybody has, where's my, wow, I have too many windows here. Where are you guys? There you are. Okay, any questions so far? I know I'm rushing through, but okay, so let's go back here. Okay, so this was our diatonic scale in mean tone temperament and other scales, 12 notes and so on. Now let's see if I can go to my next slide. Yes, okay, so this is a pretty abstract diagram in 5 prime limit, what I call projective tuning space. So it's based on the prime numbers 2, 3, and 5. And it shows all the temperaments, all the regular temperaments. The equal temperaments are labeled with numbers. So 12-tone equal temperament is here, 19 is here, and 22 is here, and so on. And they're arranged according to how they temper the primes 2, 3, and 5 relative to one another. So this line here that where you see 12, 19, 31, and 7 way over here, this is the mean tone line. All of the equal temperaments on this line temper out 81 over 80, so they are technically mean tone temperaments. And this is a straight line because that is a linear relationship among the primes that has to hold for 81 over 80 to vanish. So now we're going to look at another scale, and it sounds like you guys have some familiarity already with porcupine. This is porcupine 8, the 8-note porcupine scale. And I know some of you will hate me for this, but I have an excuse. I'm using the letter H here. And I know that H means B flat for many of you Northern Europeans, but here it does not. Here it's another note. It's below A, and that way you get this porcupine scale shown here, A, B, C, D, E, F, G, H. So there are 7 large steps and 1 small step from H to A. Now here's the lattice diagram, and if you were to try to construct this in just intonation, you would find that if you play a chord progression, starting with this chord and then going to this chord and so on, keeping the common tones, when you get back to the same chord you started with, this would be like a G major chord, G, B, D. When you get to this G, B, D, if you're using just intonation, that'll be about a quarter tone away from the one you started with. The ratio is 250 over 243. So porcupine is the system that tempers out 250 over 243, or makes it vanish. And let's go back to here. So here you see, so this line here is the porcupine line. 22 is on there, 7, 15. And here in this horogram, you see the 7-note ring, the 8-note ring, corresponding to this 8-note scale, the 15-note ring. And in the 15-note ring, we start to get, I used these up and down arrows, so V for like down, and up arrow for up. So in the 15-note ring, D, and then E down, and then E, and then F down, and then F, and so on. And then a 22-note ring with both E down, D up, between D and E. So this is yet another notation system. This is a very unconventional notation system, but it can be very convenient in certain circumstances. Let's say if you have an instrument with the 8-note scale laid out on it, this can be convenient notation. So, and here's a kind of a generalized keyboard layout for this porcupine scale in 22-tone equal temperaments. So the numbers here are just from 1 to 22, or from 0 to 21. So they're labeling the 22 notes in the tuning. And this this keyboard layout is based on porcupine. So I don't have time to explain that too much, but what you see here is porcupine 8 scale in green, porcupine 7 scale in blue, and another porcupine 7 scale in red. And 8 plus 7 plus 7 is 22, so you have all 22 notes accounted for there. So this type of keyboard would map very nicely to that notation system, where you would kind of go A, B, C, D, E, F, G, H, and then your ups and downs above and in the blue and red keys. 22-tone equal temperament supports a lot of different temperaments, even here in the 5 limit. So one of them is called Magic, which is this line here with 19, 22, 16, 25, and that has a major third generator and an octave period. So this is what a keyboard there would look like. And as you can see, if you go from note 0 to note 0, you're almost dividing the octave into 3 equal parts as you go across. 0, 7, 15, 0, or you could go 0, 7, 8, 14, 15, 16, 0. That would be a Magic 7 MOS scale. Okay, let me go back to the paper here, because now we're going to add another prime number into consideration here, which is 7. So now we're looking at 7 limit, and we're going to add these colors here to represent some of the 7 limit intervals. So the previous colors retain the same meaning as before. And then now we have like 7:4 ratio is green, 7:5 is cyan, and 7:6 is yellow. And then here is, so this is what we call a major tetrad, which is kind of like a dominant seventh chord, but much more concordant. And then the upside down version of that. And then the 7-limit tonality diamond depicted here. Tonality diamond, of course, being something Harry Partch talks about in his book. So now we can look at the decatonic scale that, or there are two different decatonic scales actually that you can find in the 7-limit. And these have a lot of these tetrads that we just looked at, these consonant tetrads. So this is kind of just showing all of the tetrads together in the scale, including repeated notes that differ in just intonation but become the same in Pajara temperament. And this is showing that some of the notes are 50/49 ratio apart, and some are 64/63 ratio apart. So if you temper out both of those ratios by adjusting the primes so that those become unisons, you get Pajara temperament. And that has MOS scales of 2, 4, 6, 8, 10, 12, 22, 34, 46, and so on notes. The 10-note MOS here is what we're showing here, and here's a lattice where it repeats, kind of like we saw before with the diatonic scale repeating and the mean tone lattice and the porcupine lattice repeating. So this scale called a symmetrical decatonic scale, and here we're using a notation system for 22 that uses just the 10 numerals, and I'll show you later how that works. But basically what you see here is that the different copies of the symmetrical decatonic scale in just intonation would be separated from one another by these ratios we talked about, 50/49, 64/63. And if you combine those two ratios, 225/224, tempering those out takes you from just intonation to Pajara temperament, and that makes all of these notes just 10 notes instead of multiple transpositions of 10 notes. They're all the same. I think I can go back to my slide now, and let's see. Yeah, so here's another decatonic scale. It's called the pentachordal decatonic scale, and it's just one note different from the symmetrical decatonic scale. So here's a lattice of that, and now this is the notation system I was talking about. So this is a keyboard, and some people have actually built a keyboard like this, or modified a standard keyboard so it looks like this. Kalle Aho from Finland did it, and so did William Lynch. This is William Lynch's keyboard here. But here we can see that the 10 numerals, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, how they're arranged among the 22 notes. So basically you have 2 steps, 2 steps, 2 steps, 2 steps, and then 3 steps from 5 to 6, 2, 2, 2, 2, and then 3 from 0 to 1. And then you can actually work out what the decatonic key signatures are for both the symmetrical and the pentachordal decatonic scale using this notation. So that's what's shown here. And this is in the paper as well. It's in 2 of my papers, actually. And here's a different kind of keyboard layout for that. Here it would be the purple keys would correspond to the pentachordal decatonic scale. And they're in order of pitch from left to right in these diagrams. The generators go up and down. Pajara, as you may know, has a period of half an octave. So what that means is that it's hard to see, here, but this number here is actually 11. It's covered by black, so you can't see it. But between 9 and 13, there's an 11, and that's exactly halfway between this 0 here and this 0 here. So that shows you that rather than repeating every octave, it actually repeats every half octave. And then the black keys here give you a super pith 5 scale, and the white keys give you a super pith 7 scale, if you know what those are. If not, you can read about them in some of my other papers, like the Middle Path. So yeah, so we saw 22, and we saw that 22 in the 5 limit lies on a lot of these different temperament lines. And then rather than the primes 2, 3, and 5, we can use, let's say, the primes 2, 3, and 7. And here's your 22 tone equal temperament again. And this line here is actually your super pith, or it's also called Archie, in this case where prime 5 is not being used, this line. So you have your pentatonic scale, 7-note scale, 12, 17, 22, and so on. That's generated by the perfect fifth and has an octave period. And here's a keyboard layout based on that, with the keys colored exactly the same way as before. They're just laid out differently. And this is a sort of a super pith-based layout here. But the symmetrical decatonic is still here in purple. You see now it's split into 2 pentatonic scales, because you can do that. You can split the decatonic scales into 2 pentatonic scales. And here's another layout, which, I don't know, this might be preferable for some people. And again, you have pentachordal decatonic on the purple keys. Other systems that 22 tone equal temperament does a good job representing. One is called Hedgehog, double wide, and this one called Astrology, which is an 11 limit. It's not in any of my papers yet, but if I do part 2 of the Middle Path, it'll be in there. So now I'm going to take a quick break to see if anybody has any questions. And yes, Stephen.
I had a question about the projective tuning space graph. And
yeah.
I believe I've asked this question before, but I haven't asked it very well. Is there a version of the projective tuning space graph that only includes equal temperaments with like a major third patent vowel being the result of an addition of perfect fifths? Or is that really kind of a nonsensical concept? I just know that I see 17 and 22 on the line, but I've heard it said that those aren't mean tone temperaments. But really, according to this graph, what the 17 and 22 mean there, of course, is that 17's like super major third ends up being that stack of fifths, and then 22's super Pythagorean ends up being a stack of fifths. But is there,
yeah, so I think,
like, what's the deal there?
Sorry, I missed the end of that.
Oh, that's okay. I was just asking, so what's the...
Yep.
Yeah.
Okay, so I think we're talking about 5 limit projective tuning space.
Yes.
And this is the mean tone line we were talking about, right?
Yes.
I don't know if I can hear you. Are you talking, Stephen? Make sure I can hear you.
I'm listening.
Yes. Great. Okay, terrific. Just making sure. So yes, we talked about how this is the mean tone line, but notice that it goes past 12, which means now we're going into widened fifths instead of narrowed fifths. And we're talking about, yeah, major thirds that are wider than in 12 equal instead of more pure. I forgot to mention that in these graphs, the center is just intonation. It's where everything is pure. And the further you get away from the center, these larger and larger hexagons, the greater the errors or mistunings relative to just intonation. So you see 17 here, and the mistuning, the 5-limit mistuning is pretty bad. But there's another 17 over here, and it's also pretty bad. So what does this mean? Well, the 17 over here is understood to have that, that wide major third mapped to the 5/4 ratio, whereas this 17 is based on understanding the sort of neutral third of 17 to be mapping to the 5/4 ratio. So I think that begins to answer your question, Stephen. Was there more to it?
No, I think that's it. I think I got it.
Great. Okay, cool. So I do need to step away for just 2 minutes. I'll be right back. Apologies, and talk amongst yourself.
Okay, I just wait for asking. I want to ask for the what the size of the numbers means.
Yeah, you mean the graphical size?
Yeah, that's. I think that has a meaning.
It must have, of course.
Are you talking about the projective tuning space graph?
Yes, of course.
Gosh, I think I'm going to remember this wrong, but the tilt of it has to do with how it's tuned. And I think the size is purely cosmetic. Like, the more important the number is, the larger it is. But I could be wrong, especially on that second one.
Hans, maybe you can comment on the horograms for people. We have also listeners that we don't know who they are. Welcome to all our listeners.
I think this is a little bit too less time because in my talk in the afternoon, I plan to explain a little bit more in detail and in as simple as possible what is the idea of moment of symmetry and what are the origins of that. And of course, the horogram is just one graphical way how to graphically depict different scales of the same MOS or different patterns of the same MOS. Or of the same MOS type, and every MOS type has a certain name given from somebody or whatever. And of course, as you have heard before, there was one interval. It's named the generator, and of course the octave is the period. And generally, MOS theory you can see as a type of generalized conception as the circle of fifths, but instead of fifths, we can have every type of intervals and generate scales with it. That is really very brief.
Yep.
And
thank you.
So, yeah, I will explain for in my talk after the afternoon. I will explain here for our people more about the general idea of MOS and things like that, because then maybe it explains your approach much better. I had a question: what parameter is described in this projective tuning space with the size of the numbers?
Oh, that's just the smaller the number, the bigger the font. That's all. So it's just meant to make the simpler equal temperaments stand out, make them easier for you to see. That's all it is.
The
And,
higher, the smaller it is.
Sorry?
The larger the number, the smaller the number. The smaller the number is in the diagram.
Font, yeah, exactly.
Okay, then I know that.
Yep. So yeah, we were talking about various two-dimensional systems which can be defined by a period and a generator. And in the case of mean tone, we had a period of an octave and a generator of a fifth. In the case of porcupine, period again was an octave. The generator was sort of a step, a neutral step between a major and minor second. And then we talked about the decatonic scales, Pajara. That's based on a half octave period. Period is half an octave, and the generator can be understood to be like a minor second, or it can be understood to be like a perfect fourth, perfect fifth. Those all end up equivalent modulo the half octave period. So now we're going to move on. We're going to leave octave equivalence behind. We made this assumption of octave equivalence, but now we're going to drop that assumption and go to the Bohlen-Pierce world. Yeah?
Paul, I think you have to share again your screen.
Okay.
Yeah, you had this already, this page with the Bohlen-Pierce.
Yep. I'm going to do that. And I already forgot. Okay.
Again, it stopped the sharing.
It stopped sharing?
Yes.
We see that what is active in your window, your own window, your own screen. So you have
it's not shared in the moment.
Yeah, not
sharing,
but when you share, we see that what you have active in your window.
Yep.
Now it's shared, and yeah, okay.
Yes, activate. Yes.
Okay, good.
Sorry, by the way, I think we had a question here by some of our listeners we don't know, just a fellow Jitster.
Sure.
Him or her to send something on chat, but maybe there's now the chance for just this fellow Jitster to ask the question.
Sure.
So let's wait a second more. Otherwise, fellow Jitster, please send your thoughts in the chat, and then we can react later to it. Thank you.
Okay.
I think, Paul, you can continue.
Okay, so now let's talk about Bohlen-Pierce. So Heinz Bohlen from Germany and John Pierce from the US, independently from each other in the 1970s, came up with this idea having to do with using only the odd harmonics. And in the case of Pierce, he was interested in timbres like square waves and triangle waves that have only odd harmonics in the spectrum. And the sort of idea that they proposed was that in an environment with those kind of sounds, where there are no even-numbered harmonics, no second harmonics, the 2-to-1 ratio, which defines the octave and octave equivalence, might not be as important, and we might instead begin to perceive equivalence at a 3-to-1 ratio. So that's the concept behind Bohlen-Pierce, and specifically, it's the 13th root of 3, so 13 equal divisions of 3-to-1. 3-to-1 is usually called a 12th, perfect 12th. But in the Bohlen-Pierce world, it's called a tritive because it sort of replaces the octave as your new interval of equivalence. So as you can see, these letter names, which were assigned by Heinz Bohlen from Germany goes C, D, E, F, G, H, J, and then A, B, and there's some sharps as well to make the 13. So both Bohlen and Pierce, independently of each other, found this 9-note scale within the 13, and I'll be showing you a little bit about that, why that's special. But I just wanted to jokingly point out that I plead innocent about using this H because Heinz Bohlen was himself Northern European, so I can get away with it if he can. Anyway, here's a lattice, and now these lattice rungs are different than before because instead of octave equivalent, they're tritive equivalent. So this purple vertical line here represents a 3-to-5 ratio or a 5-to-9 ratio because 3 and 9 are now equivalent, tritive equivalent. And then the green here now represents 7-to-3 or 9-to-7. And then this cyan would be 7-to-5 or I guess you could make that 7-to-15 would be the tritive inversion of that. And you can see the 9-letter names here, A, B, C, all the way through J. Bohlen skipped I because it looks too much like a 1. And it forms this lattice. And this lattice repeats infinitely, just like it did for the mean tone diatonic and for the porcupine scale. If you were to try to construct all of these intervals and chords in just intonation, what you would find is that any note is different from the next nearest instance of that same note by a ratio of 245 over 243. So if you are in, okay, so now we're in 3-5-7 projective tuning space. And now these numbers represent the number of notes per tritive. So here, right near the middle, you see this 13, which explains why Bohlen and Pierce were so attracted to this. It really comes very close to nailing just intonation ratios based on the primes 3, 5, and 7. And then this line here corresponds to 245 over 243 vanishing. And so 13 equal divisions of the tritive will do that. So will 9. And 9 is our, remember, the number of notes in the diatonic Bohlen-Pierce scale. So that's not surprising that would appear on this line too. Now, here's a horogram for, so this scale is called the lambda scale, this 9-note scale in Bohlen-Pierce. It's called lambda. That's what Heinz Bohlen called it. And accordingly, we say that when 245 over 243 vanishes, we are in lambda temperament. So we can construct a horogram for that. Now, of course, making a comma vanish, there are different ways of doing that. One approach is top. It's basically how you distribute the comma over the intervals in some sort of optimal way. Top being one definition of optimality. So here you see 1903 cents, 1,903 cents. So that's a perfect 12th, basically, is your period here. And the generator is about 440 cents. And you get MOS scales of 1, 2, 3, 4, 5, 9, 13, 17, and so on, notes per tritive. Now, I've stripped away the outer rings here and put the note names that we were looking at before so we can see more clearly how this lambda temperament goes. lambda scale, the 9-note scale, A, B, C. It's kind of easy to remember. E is in the center, and it kind of goes 1. If you look at the 13-note ring here, it's 1 step from E to F, and then 2 steps from F to G, 1 to H, 2 to J, 1 to A, 2 to B, 1 to C, and 2 to D, and 1 to E. So it just alternates 1 step and 2 steps. That's sort of this 9-note diatonic, pseudo-diatonic, or lambda diatonic scale. And in this tuning, since it's not 13 equal, but it's the optimized 2-dimensional version of lambda, you'd actually differentiate between G flat and F sharp, which were, if you recall, they were the same in the original 13 equal division. Well, they don't show you the flats here, but they are the same, whereas here they're not the same. And let's go back to this graph here. So we see 13, and what else do we see? Well, 35, that's not too far away. That's not going to be too bad if we try 35 divisions of the tritove. And then one thing about these graphs is you see the fonts are slanted. Some are tilted a little to the right, a little to the left. If it's tilted to the right, it means it's advantageous to stretch everything slightly. Makes all the harmonies closer to pure. So let's try to use this 35 equal divisions of the tritove, slightly stretched, for our Bohlen-Pierce lambda scale. Oh, this is what I was talking about before, and I skipped. I didn't show this to you, but yes, F sharp and G flat are the same when you use 13 ED3, 13 equal divisions of tritove. But now let's try the 35. And 35 equal divisions of a slightly stretched tritove gives you, well, if you recognize these sense values, it's 22 equal again, 22 equal divisions of the octave. So you can actually play the lambda scale or the Bohlen-Pierce diatonic scale in 22-tone equal temperament, believe it or not. E, F, G, H, J, A, B, there it is. And then now you not only have a 9-note scale, MOS scale, you also have a 13-note MOS scale with 2 different step sizes, 164 cents and 109 cents. Very familiar for you 22 Edo experts. And you also have a 22-note scale, 22 notes per tritove. And this has steps of 109 cents and 55 cents. So basically 2 degrees of 22 and 1 degree of 22 in this pattern. So I thought that might be something new for most of you that maybe you didn't know before. And I have a lot more materials here, but I think we're running low on time. So I think I'll go back to questions, and then we'll try to wrap it up.
Yes, thanks a lot. Amazing stuff. So please, questions.
Can I have questions? Yeah. Thank you very much, and that was a really surprise. I have never thought about that. That lambda, the lambda scale is fitting into the 22 EDO. Of course, we know all that of course 41 EDO is perfectly matching with Bohlen-Pierce and 12 EDO in some way, but that is absolutely new knowledge of it. Of course, maybe one comment. If I'm maybe it's just a formality, but if you write, if you point out in Boland Pierce a TOP tuning, maybe we have to change the middle letter to TTP tuning, tempered Pichita.
Yes, yes, you're quite correct.
And the other thing, maybe there is of course a little information in the internet and about the node names. As I now, I couldn't found it also in the moment on the Boland Pierce side. As I remember, the first node names what Boland developed starts from KLM and OPQRS for the I think for the delta scale, not for the lambda scale. And of course, later Boland used also this C, D, E, F, G, H, ABC. What I use a lot, and but I think these letters with the H and the B, it goes back to an initial idea of manual optical from Huygens Fokker Foundation in the Netherlands, as I remember in the right way.
Well, he's definitely a good friend of mine, and we've worked together a lot. But as far as I know, the A, B, C, D, E, F, G, H, J notation does come from Heinz Boland. So
it comes from Boland, and of course, but then I don't know the exact information, because it seems what I read from the Boland Pierce site, it seems maybe Heinz Boland was doesn't want to show his authorship. Maybe he was so shy, and unfortunately there's not anymore any option to ask Boland. He passed away 2018, and
yeah.
As I think here on the site, as I remember it, he claimed that it is an idea of a manual optical.
Yeah. So here's the BP site, Heinz Boland's website, and here you see the C, D, E, F, G, H, J, A, B, C.
Yes.
But yeah. I don't know if I missed a question. Hans, did I answer everything?
Yes, yes, you answered it.
Okay, so let's go to Stephen.
I was just wondering what TOP lambda, like which intervals from 3, 5, 7 space does it temper, and in what way? Like what advantage does that give you over just tuning it to a standard tritave?
Well, it's similar to why top mean tone has a stretched octave. It's a way of, and actually, you can tell right away from the ratio. The ratio is 245 over 243, and you want to make that vanish. Now, 243 is just a power of 3. So if you want to make 245 and 243 the same, you have to make 3 larger, because 243 is just 3 to the 7th power or something. So if you make 3 a little bit larger, then that 243 is going to get larger by just the right amount to equal 245, and that's what you need. So that's a quick way of understanding that the tritave likes to be a little bit stretched optimally in lambda temperament.
I see. Thanks.
Kenneth, are you raising your hand, or are you just?
No, just scratching my head.
Okay. Okay. Well, I did have a lot more slides, but I think I've pretty much used almost all of my hour, and I'd like to get some sleep so I can rejoin you guys in about 6.5 hours for the performance, and then maybe after that there'll be some more discussion if any more questions occur to anybody. I'm going to put another link in the chat window here where you can find more of my papers besides just this one. And encourage everybody to think of me as a perpetual resource